Okay, this continuation of 5.1, we're looking at probability, and we want to know why the following is not a probability model. Okay, if you were to take and add up all of these probabilities, so the sum of all these probabilities, it would equal 1.2. And 1.2 is greater than 1, and so for this reason, the sum does not equal 1. It has to sum up to exactly 1. And since a probability model here, since this model adds up to 1.2, it cannot be a probability model. Okay, now if an event is impossible, the probability of that event is 0. If an event is a certainty, that probability is 1, as I mentioned in the previous video. So the closer probability is to 1, the more likely the event will occur. The closer the probability is to 0, the less likely it is to occur. So for example, an event with probability 0.8 is more likely to occur than an event with probability 0.75 or 75% if you want to think of them in terms of percent. Okay, a probability with 0.8 will occur about 80 times out of 100 because 0.8 is 8/10 or 80 hundredths. So it occurs about 80 times out of 100 repetitions of the experiment, whereas a probability of 0.75 will occur about 75 out of 100 times. So we can see why a probability closer to 1 is more likely to occur. Now, be careful with the interpretation. An event with a probability of 0.05 does not have to occur 75 times out of 100. Rather, that is what we expect the number of occurrences to be. We expect it to be close to 75 and 100. The more repetitions of that probability experiment, the closer that proportion with which the experiment occurs will get to 0.75, and that's the law of large numbers. Now, one of the goals in this course is to learn how probabilities can be used to identify what we call unusual events. So an unusual event is an event that has a low probability of occurring. And we're going to talk more and more about those unusual events, but that's going to be something we look at, especially towards the end of the course. Well, and kind of in the middle. You know, if something happens and the probability is less than 5% or 0.05, then we're going to say that's a pretty unusual event. And so it might merit some further research. So in this question, I've got snuck right in here, question number 12. Which of the following numbers could be the probability of an event? Okay, 1.5 is too big because, again, probabilities must be within 0 and 1 inclusive. So 1/2 is good, 3/4 is good, 2/3, 0 is impossible as far as the event occurring, but that's still a probability, so we're good. Negative probabilities, no way. Okay, so it is that quick to identify whether it could be a probability or not. It has to be between 0 and 1 inclusive, meaning 0 and 1 can also be true. Now, probabilities deal with the likelihood that a particular outcome will be observed. So for this reason, we begin our discussion in probability and determining probabilities using the idea of relative frequency that we have looked at in the past several times. So probabilities computed in this manner rely on empirical evidence, that is, evidence based on the outcomes of our probability. So the probability of an outcome E is approximately the number of times event E is observed divided by the number of repetitions of an experiment. Okay, so the probability of E is approximately the relative frequency, which is just the frequency of that experiment E divided by the number of trials. Okay, so let's suppose that you toss a coin 100 times and you get 95 heads and 5 tails. Okay, it's unusual based off of what we know about a coin, but based on these results that you're seeing, what is the estimated probability for the next flip and a head? Well, we'll say based on our empirical, there we go. So based off of our empirical data, we would say that 0.95 is the empirical probability, because the frequency was 95 out of the total outcomes, which was 100, so 0.95. So this would probably be a weighted coin, an unfair coin based off of that observation. But that's, given the information that we have, that's what we've observed. Okay. So here's some other observations. So the following data represents the number of live multiple delivery births, 3 or more babies, in 2012 for women ages 15 to 54. Okay. So there were 44 women who were between ages 15 and 19, 404 between 2024, 1204 between 25 and 29, and so on and so forth. Okay, so first we want to construct a probability model for the number of multiple births. Okay, and when we construct this probability model, what we can do is I can just tack on a little bit more here. Oops. Trying to get my straight lines going down here. Okay, so this will be our column for probabilities. So what we'd first need to do is you would need to add up. We need to find out how many different results there are. So I would add this column up, and you get 4,919 if you add them up. So the probability for someone age 15 to 19 to have the multiple births would be 44. Okay, the 44 observations out of the 4,919 total observations. So this is approximately 0.009. Okay, then the next one, you would take the observed divided by the total, 404 over 4919, which is 0.082, and then you take 1204 divided by 4919, approximately 0.245, and you do that for the rest of the way down. So I would do 1872 out of 4919 is 0.381, then a 0.203, then a 0.067, and a 0.013. Okay, and so that would be those empirical probabilities based off of the results that we have from our table. So that's our probability model. Now, in the sample space of all multiple births, are multiple births from 15 to 19-year-old mothers considered unusual? And again, unusual is a probability that an experiment is less than 5% or 0.05. So is a female ages 15 to 19 who has multiple births unusual? Yes, because that probability 0.009 is definitely smaller than 0.05. So that is unusual. Okay, so in the probabilities, or in our sample space of all multiple births, are multiple births from ages 40 to 44 unusual? Okay, and in this one we would say no, because the probability there is 0.067, and that's greater than 0.05. So that would not be considered an unusual event when we use the metric of 5% and below as unusual, which is relatively standard, especially what you will see in this course here. Okay, now we're going to compute and interpret probabilities using what's called the classical method. Okay, the empirical method, again, that gives us an approximate probability of an event by conducting an experiment. Now, the classical method of computing probabilities does not require that you actually perform the probability. Rather, it relies on counting techniques. So the classical method of computing probabilities requires equally likely outcomes. So an experiment has equally likely outcomes when each outcome has the same probability of occurring. So for example, when a fair die is thrown once each of the 6 outcomes in our sample space, so you get a 1, 2, 3, 4, 5, or 6, has an equal chance of occurring. Okay, now if you contrast this with a loaded die in which 5 or 6 is twice as likely to occur as 1, 2, 3, or 4, okay, we're not going to work out quite as well there. So that's, again, we don't have to, in classical probabilities, we don't have to actually perform the experiment. We are going to use counting techniques. So, computing probabilities using the classical method. So, if an experiment has n equally likely outcomes, and if the number of ways that that event E can occur is m, then the probability of E, which is P of E, is just the number of ways that E can occur divided by the possible outcomes, or that m divided by n. Okay. So, if S is our sample space in this experiment, then the probability of E is the number of, so n of E, which is the number of occurrences or outcomes in E, divided by n of S, which is the number of outcomes in the entire sample space. Okay, so this one is a little bit more difficult to calculate because we have to count. You have to know all the possible outcomes without observing. Okay. So let's look and compute a probability here. So the sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose that all these outcomes are equally likely. We want to compute the probability of event F, which is 3, 5, 9, and 10. Okay, so now if we look at event F, okay, then we'll say the probability of event F is going to equal, okay, the number of events in F divided by the number of in our sample space. So this is 3, 5, 9, and 10 is 4 out of our sample space, which is 10. So it would be 4/10, which reduces to 2/5, or 0.4. Okay, and that would be our outcome, or excuse me, our probability. Okay. So that's a brief look at that. We will continue. I think I got 2 questions here left. We'll do that in a part 3. But hopefully this idea probably is making a little bit of sense. And again, we're just going to build more on some new examples in the next video, I should say.